All right, welcome everybody. Thanks for joining us. This presentation concerns replacement valves, manifolds, and control packages, which are field retrofittable to enhance the capability of your existing die casting machinery. The integration of throttling valves into pre-engineered manifolds that can be retrofit in the field can enhance the capability and life of shot ends made by these manufacturers and others. And the photograph that we're showing on this slide is of a new front head on an HPM die casting machine. And this would be the manifold on the rod side of the shot cylinder, which has been redesigned to eliminate the POC, HPM's proprietary throttling valve, and to accommodate instead, a much more modern design, two-way slip-in cartridge style throttling valve. And we'll talk about this in a little greater detail later in the presentation. The left-hand photo I just described, the center photo, shows a new throttling manifold on a 1,600-ton Prince machine in place of where the binary valve used to reside. And the photograph in the upper right shows a throttling manifold on a hot chamber machine, a meter-out design, and the slip-in cartridge can be seen right here, and here's the servo pilot valve. Today we'll cover what the benefits of retrofit are from both a performance and a business standpoint. We'll look at a case history of a throttling manifold integration that was done at a Toro die casting facility. We'll talk about the benefits of shot control. We'll look at some other throttling manifolds that we have done and a brief summary, and then if there's some questions, we'll try to answer those. Performance benefits, you can get an increase in shot speed capability from new throttling manifolds. It doesn't always happen, but it's not uncommon for there to be a speed increase. The efficiency of the cell is increased. Scrap typically is decreased, and with the ability to control acceleration and deceleration, we can minimize the impact force, reduce flash, and reduce wear and tear on the tooling and the die casting machinery. From a business standpoint, it's far cheaper to enhance the capability of an existing shot end than to replace it. And once the shot system has an integrated throttling manifold and shot control system, it's now capable of any die casting process, squeeze process, or vacuum-assisted process. And these are easy upgrades, field retrofittable. So let's talk about the Toro company, who has a manufacturing facility in southern Minnesota. It's a very high volume operation. It's been there for about 20 years, and like most plants, if you started out with a clean piece of paper today, it wouldn't look like the facility that has evolved after you've lived in it for a while. But Toro has managed it well and modified the plant periodically with an eye to the future. They have a very lean staff here. It's a high volume production operation. They have 7 injection molding machines, 5 die casting machines, the largest one of which is this one shown here, a 1,600-ton Prince they purchased in 1990. And this machine is typically sold out from October to June, where they're manufacturing summer season products. They have a dozen or so different lawnmower decks that they run. And at this operation, they trim, clean, and do do some painting. They also ship some decks to other Toro manufacturing facilities. With a lean staff and high volume, it's a highly automated operation, and it depends upon robustness, repeatability, and very low scrap rates to be efficient. Since Toro purchased the 1,600-ton machine in 1990, the decks have generally increased in size, and the designs that they're casting today are challenging the available clamp tonnage of the closing end of the machine. They also center shoot these decks, so there's limited space for the in-gate, and the metal has a long way to travel through the die. You'll see later we'll show a shot profile from an actual production shot, and they don't even use the intensification. They're just trying to get the metal into the die very quickly, and it's frozen off before they have time. So the 1,600-ton machine was originally purchased with a binary 2 standard 3-speed shot system. Toro upgraded the machine to add the ramping capability, and it has no low impact system. Had no low impact system. And here there's a green arrow that points to the binary 2 valve as it existed prior to the integration. Over time, Toro would develop an occasional cracked segment on the valve, which would have an impact on the fast shot velocity. They also had some issues where the segments wouldn't collapse properly, which gave them inconsistent shot speeds. The operators then were fussing with the fast shot settings, trying to maintain a stable process, and it caused a lot of variation, and they had some increasing scrap rate issues. So Toro decided they needed to make a change and considered a new shot end as an option. They decided they needed more speed to accommodate the castings that were now challenging the original performance specifications to which they'd ordered the machine. And they decided against a new shot end because it was very expensive to do, and came up with their decision, which is what they really needed, was a more robust velocity control system and more speed. So the solution was to remove the binary 2 shot valve and the manifold block on which it resides. A direct bolt-in replacement was designed and fabricated by die-cast press, and it has an 80-millimeter two-way throttling valve manufactured by Olmsted Products in a collaboration with Visi-Trak. It has a 30 GPM servo pilot valve, which you can see clearly mounted on the bright blue cover of the cartridge. It has a PO check. The manifold has a PO check to release oil from the main area so that we can retract the cylinder. It has another cartridge to develop pressure on the rod side to retract the cylinder. And there's an inline, no bypass pressure filter that gives a final filtration of the oil that's going to pass through the servo pilot valve. And here's a shot of that manifold block. This is a direct bolt-in replacement. The servo pilot valve is an excellent design. It's manufactured by Textron. They're located in Southern California. It is a unique design for a servo valve in that there's no hydraulic fluid flowing through the first stage of this valve. Traditionally, servos have had hydraulic fluid in the first stage that's directed to either the A or B port on the little four-way valve in the second stage through very, very small orifices that have been points of contamination and points where contamination can clog up the servo valve. This Textron RDDV design eliminates hydraulic fluid from the first stage, and instead there's a torque motor connected to an elliptical, and as we apply current to the torque motor, it rotates, thus moving the elliptical and thereby shifting the spool in the four-way valve to direct flow to either the A or the B port. So with this design, the point in the servo valves that have traditionally caused them to be fussy is completely eliminated, and we have instead a very robust design that has been a proven winner in the die casting environment over the last 12 or 13 years. The throttling manifold arrived at Toro on a Tuesday morning. Toro's own in-house crew did the installation. By Thursday afternoon, the manifold was bolted in place. All the original connections, which had been replaced, new fittings, were reconnected to the manifold block. And then this piece of high-pressure pipe that carries the discharge oil from the rod side of the cylinder down to the throttling manifold, this new pipe section had to be fabricated because the inlet to the manifold had moved 3 inches further away from the closing end of the machine with the new manifold block design. And Toro also elected to replace the rack and pinion encoder with a Visi-Trak tail rod in the form of a 1-inch diameter rod, and did a very robust mounting of that. So the total installation was less than 3 days at Toro. And here's a quote by Dave Brockman, who's the engineer at Toro. "The new Visi-Trak valve increased our top speed by over 100 inches a second and has made it possible to continue creating cost-effective castings even after we outgrew the original capability of the machine." Toro had retained the original runoff documentation from prints. And in 1990, with the binary valve in the full open position, at an 800 psi accumulator pre-charge, the machine dry cycling would achieve 157 inches a second peak fast shot velocity. At 1,000 psi pre-charge, it would do 186. At 1,200, it would do 208. When Toro charged the system up, the accumulator had 1,340 psi pre-charge, and with a 100% open loop command to the throttling manifold, the machine now had 309 inches a second velocity capability. So, granted, that's not a perfect comparison. A 1,200 psi pre-charge would have provided a perfect comparison. They probably wind up with another 80 or 85 inches a second at a 1,200 psi versus the binary valve. So they had a substantial performance increase. And here's a shot profile that I referenced earlier. They do a closed loop motion block to cover the pore hole, closed loop motion block in the intermediate phase, and then they do an open loop fast shot motion block. And you can see as the system extends, the piston is moving out, so the whole hydraulic system is extending. As it does so, it loses power, and you can see the fast shot velocity gently tapering off. Had Toro elected to use a closed loop motion block here, that wouldn't have happened. But a good-looking shot profile nonetheless, and you see here, no intensification. The machine has an intensifier, they just don't employ it for making these big lawnmower decks. So here is an X-bar chart, an average velocity was calculated from 10 inches to 15 inches of stroke. For 135 consecutive shots, there was a total range from the slowest average to the fastest average of 0.49 inches per second, yielding a CPK of 9.05. This is an extremely capable machine. Then we did an X-bar chart on average velocity during the fast shot. Because this was an open loop motion block, there was a bit more variation here, but nonetheless, it was very repeatable. And we did another X-bar chart on fast shot rise time. This was the elapsed time for the shot cylinder to accelerate from 35 inches a second to 190 inches a second. And there was a total variation of less than 1 millisecond in the rise time for 135 consecutive shots, once again yielding a very capable machine. And here's a screen showing the calculator program. It's a process calculator program. And we show down here the deck Toro's making and the process that they've identified in the calculator here. Shows they need 1,666 clamp tons. So they're just, challenging the very limit of the tonnage capability of this press. A post-audit of the installation revealed that they're now able to easily make all these lawnmower decks on the machine that they have. They have outstanding velocity control. The overall equipment efficiency increased by 15.5%. They had a pretty significant scrap rate reduction. Now, it was already a fairly low scrap operation, but they were able to reduce the scrap even lower. They've largely eliminated flash from these big lawnmower decks, and the total integration cost was about 40% of the cost of a new shot end. And another quote from Dave Brockman: the retrofit package in Visi-Trak 2 has given us a shot system with outstanding control and performance. This economical solution extended the service life of the machine and helps us continue to make cost-effective castings after they have outgrown the clamp tonnage capacity of the machine. It's a lot of bang for the buck. Can't say it any better ourselves. This screen shows a modified packing retainer gland, which is accommodating the Visi-Trak sensor. The piston rod on the machine has been modified, and then this packing retainer gland design by die-cast press is excellent. It involves a long bearing surface that extends back into the cylinder, which eliminates any sagging of the shot cylinder as it extends outward. It means then that the rod traverses back and forth in a very straight path, and this bronze block that you see can easily be removed so that the bidirectional transducer can be installed and gapped properly, and then that bronze block can be reinserted into that the nose of that packing retainer. You'll also notice there's a metallic wiper ring that, as the rod traverses forward and backward, it's keeping the area underneath the packing retainer free of any sort of flash or blowback that occurs. And this is an outstanding design for accommodating the bidirectional transducer. It ensures that it's robust, and it's not uncommon for the actual sensing element in this particular design to last for 10 years. Many machines have a tail rod on them, and the most immediate, cost-efficient way to integrate a Visi-Trak sensor is to replace the existing tail rod. Once again, we have a very nice design by die-cast press. You see here in the photograph on the right, there's a bearing block which has a bearing pressed into each end of the block. This guides the tail rod very straight as it traverses back and forth. This block has zerks on it so you can grease those bearings. And then in front, a bronze block shown in the photo on the left. The front side is painted. The photo on the right, the back side is unpainted. That's a bronze block. It accommodates the bidirectional transducer. And then at each end, this end of the bearing block, and then this end in the left-hand photograph, the front face of the sensor mounting block, those also have those metallic wiper rings on it, which keeps the rod nice and clean and prevents any type of stuff from the foundry from getting underneath the bidirectional transducer. Also shown in the left-hand photo, the puller bracket, a good, strong design by die-cast press. So we've shown in this slide a superior design for Visi-Trak sensor installation on the cylinder rod, and here a superior design for installation of a Visi-Trak sensor in the form of a tail rod. Our SureTrack 2 shot control system is our 5th generation of closed-loop motion controller. It is really just a beautifully refined product now. Earlier generations could require that a technician check various points with the voltmeter. Now all the diagnostics are done right from the user interface, pushing buttons on the keyboard, including nulling of the servo valve. All the tuning is done digitally today. There's no pots to adjust. So this is really a nicely refined system for the die casting application. The benefits of integrating control are to take advantage of Ohio State's 1991 research that showed the ability to minimize air entrapment during the slow and intermediate phase with a constant acceleration ramp. You can create any shape injection profile to result in smooth metal flow, outstanding repeatability. It has the ability to decelerate the system to reduce the impact spike. It's programmable in engineering units, not 2 turns of a valve, which is different for everybody, but actually programming the control and engineering units, which are easily stored on the computer and easily recalled to set the shot end up again. And it's easy to retrofit onto existing machines, or you can specify it on your new die casting machine. And here's an example of how to program a shot profile. We're telling the control to accelerate from 0 to 80 inches a second over 16 inches, and to maintain that velocity to 17 inches. And then the next second motion block, we're calling for 250 inches a second, as quickly in a closed loop mode as the system will accelerate. And at 25.5 inches, we're closing the throttling valve to decelerate the system. There's the resulting event. And the SureTrack 2 has 2 axes of closed loop control. And we use the second axis to provide a programmable pressure control during intensification. And we're using a special command to get the system to react as quickly as possible. So we're telling it to go to 3,500, but our actual target is 2,000 psi, and hold for 600 milliseconds. And here you can see it's right at 2,000 psi for 600 milliseconds. Then we asked for 2,500 and hold for 600. We asked for 3500 at the end and hold that for 700 milliseconds. So there's our programmable event, all done in engineering units. Here's another shot profile display where we're plotting on top the command from the control to the throttling valve in blue, and then the LVDT response from the throttling valve in white. So you can very clearly see how the response from the LVDT very, very closely follows the command, and of course the resulting velocity profile looks essentially like the command signal. Here, the command to decelerate the system, close the valve, and here you see the valve closure happening 4 or 5 milliseconds later and bringing the shot system to a gentle landing. Here's 10 shots overlaid. And here's 3 different shot profiles. The one on the left from a 2,500-ton Hydra at a 250 millimeter bore shot cylinder, was capable of accelerating from approximately 11 inches a second to 327 inches a second, a delta 315 plus in 16 milliseconds. I'll show you the picture of the throttling manifold that generated this performance. Then the upper right is a 1,750 metric ton Z-tie machine that has our throttling valves and shot control system completely integrated into the machine. You're seeing almost 13 meters per second velocity here, but once again, excellent acceleration and deceleration capabilities. Here's a shot profile from a German customer that uses a long, slow shot as they pull a vacuum on the die, and then a very short, fast shot to inject the metal into the cavity area. Once again, excellent acceleration and deceleration capability. So let's look at some other integration designs. This is the new front head on an HPM machine. This particular one is on a 900-ton machine. It eliminates the POC, which it was a proprietary HPM design. It performs pretty well when it's new. The POC does. The very low-speed shot control isn't as good as this Olmsted two-way servo-piloted valve. And, you know, the POC doesn't hold up as well. It's a design from yesteryear that has just been very much improved upon by the genius of Pete Olmsted. So this new front head is a die-cast press design for an HPM Model 2 or newer shot end. It eliminates the POC. It integrates the Olmsted two-way standard slip-in cartridge throttling valve, which is easier to tune, more robust, and has better velocity control. So a field retrofittable package. Here's looking at 180-degree opposite view. It's not easy to see from this particular photograph, but the rod side of the HPM cylinder has been reinforced with that long bearing surface at the rod end that I previously described that ensures that the rod traverses back and forth in a very straight path, and they've integrated the Visi-Trak sensor directly onto the cylinder rod. This shot end will give them years of trouble-free service. So the advantages of the new front head, once again, eliminates the POC, integrates a standard two-way slip-in cartridge valve that has been designed for this die casting application and goes like a rocket. It's very robust. There's outstanding velocity control throughout the entire speed range of the machine. The reinforced packing retainer gland ensures not only a robust and long life to the cylinder, but it makes the rod traverse back and forth in a straight path, and therefore the Visi-Trak sensor then becomes an extremely robust velocity sensor. This is an image of the throttling manifold for the 2,500-ton Hydra. We showed a shot profile from this previously. The manifold bolts directly to the exhaust port on the Hydra cylinder. This bolt pattern matches up to the exhaust port on the Hydra shot cylinder. And it resulted in a machine with excellent velocity control and really fantastic acceleration and deceleration capability. There's the event. A delta 8.3 meters per second, that's 330 inches a second, roughly, acceleration in 16 milliseconds. This is two images shown here of an inline design. It is a 50 millimeter two-way throttling valve in a cast steel body. We see here the mounting footprint for the servo valve, and this valve facilitates the hydraulic integration on some shot end designs. It's shown here on the right, integrated onto a Wozniak shot end. Those of you that have a Wozniak shot end, you'll be familiar with this. The speed valves for slow and intermediate are removed from the manifold, the rod side manifold. Covers are made for those. And then the fast shot valve is removed. And then the two-way throttling valve is mounted at the discharge port for the fast shot valve. So now all of the oil exiting the rod side of the shot cylinder must pass through this valve to get back to tank. So the entire shot is controlled by modulating the discharge of oil through this throttling valve back to tank. Very inexpensive means of integrating an excellent velocity control system onto an existing piece of hardware. Here's a shot end designed and manufactured by Die-Cast Press. It's bolted to the casting that is part of the UBE design for connecting the shot cylinder to the closing end of the machine. The customer was happy with the upper half of the machine, which was still in good shape, but needed a better shot end and better velocity control. They achieved that with this new shot end integration designed by Die-Cast Press. And here's a Die-Cast Press shot end. This resides in Visi-Trak's facility in Cleveland, Ohio, and we use it for training, for testing new valve designs, and it's been an invaluable piece of equipment. In addition to the 4 examples of integration that we've shown, which was the Prince, the HPM, the Hydra, and the Wozniak, throttling manifolds and Visi-Trak controls have been engineered and installed on Toshiba, Cox, Triolzi, Agrati, B&T, Weingarten, Bueller B-Series machines, and quite a few others. In summary, the integration of new throttling manifolds enhance the capabilities of the existing shot system. They are field retrofittable. The flexible control lets you run any injection profile. It's typical that a velocity increase in the shot system can result, and it's always less than half the cost of a new shot end. And finally, Visi-Trak has developed an HMI, which is a graphical interface to the PLC. It's an option to any SureTrack 2 or Visi-Trak 2020 monitoring system and lets the user run the entire die casting machine from their Visi-Trak system. Lets you control the entire cell, easy to set up and save those setups. When you save the setup, it's automatically backed up to the data archiver, and there's ladder logic display available, and it's a very cost-effective replacement for your existing systems which are reaching the end of their life cycle, such as a Pro Manager or HPM's HMI.